derivatives tells us. So you've learned that basically in the first derivative test that if you have a function like let's say like x squared plus e to the x, you know that if you take the derivative of this equation that you get 2x plus e to the x. Now, unfortunately, for something like this, it would be very tough to try to figure out, when is this equal to 0. But in either case, what you can do is you can kind of tell that that for values that are positive, that this will always be positive. So in this case, it is possible that this function may actually never be 0 for that matter. But let's say, for example, that I wanted to know like the second derivative. Well, if I take the second derivative, I get 2 plus e to the x. But then if I take, like the next derivative, I see that basically I end up with just e to the x. So after that, I notice that any other higher order derivatives, it'll just be e to the x. Okay, but what we can probably do instead is just kind of focus on just the first derivative and second derivative. Now, one thing that we can do is look at, for example, like just looking at the second derivative only. Now, when we look at the second derivative, we tend to just really look at what is called concavity. So concavity is essentially when you have a function of which might have a curvature that looks something like this. So essentially we have that for like over here, we have that the second derivative is going to be positive. But if we look at like over here, we have that the second derivative is actually negative. And then similarly, we have that over here, it's positive. Okay, now there are ways to find like whenever this happens. Okay, so essentially we have that for concave down, we'll just use something like that. And for concave up, we'll just call that. Now, let's say, for example, that we look at a few functions. For example, we have that if we look at the parabola y equals to x squared, well, y equals to x squared looks something like this. But we have that basically that this is not concave down anywhere. But we also have that this is concave up from minus infinity to infinity. So in this case, we have that there never really is a point of inflection where the curvature will change. But if we look at, for example, 1 over x, well, if we look at 1 over x, looking at 1 over x, you have something like this. Well, here, this is actually way different. You have that this equation, 1 over x, it has that it's concave down from minus infinity to 0, and then it's concave up from 0 to infinity. So the inflection actually did change, but there was no inflection point. Now, similarly, you can actually look at 1 over x squared as well. Now, when you look at 1 over x squared, well, 1 over x squared, it looks something like this. Okay, well, this is concave up from minus infinity to 0, and then from 0 to infinity. So it's not concave down anywhere, but we also have that there is no inflection points either. So these are mainly just to let you know that there are many different possibilities that might happen when it comes to second derivatives. But the best thing to do is to really just look at, for example, um, a function. So let's say that we have f of x is equal to x minus 1 over x. Now, if we want to find the intervals of concavity, you basically are just going to have to find the first derivative. So, or the first derivative and second derivative. So you have f of x prime is equal to 1 plus 1 over x squared. You then take the second derivative and you find that this is going to be negative 2 over x cubed. Now the issue with this is that this is always negative for values that are not equal to 0. So in this case, this would imply that the whole thing is, okay, hold on. Actually, let's be careful with that. Yeah, so we have that there is a restriction that it cannot be 0. But, okay, so getting a little ahead. So if I was to set up an interval line test, I would basically find that for values that are less than 0, that's going to be positive. But for values that are greater than 0, it's actually going to be negative. So we have that this is going to be negative. Okay, now what this is basically saying is that we have that there's concave up from minus infinity. So we have that this is concave up from minus infinity to 0. And then we have that it's concave down from 0 to infinity. Okay, now if we wanted to find where this function was equal to, let's say, like 0, we can, and then also we can find its graph. So like if we go ahead and we look at the graph of the equation, let's say that, we have x, we have minus 1 divided by x, and then we go to graph. Let's actually make sure that that knows that I mean 1 over x. Let's just delete that, delete, and go to graph. Let's see. There we go. So we have that this is our graph of our equation. We have that it's concave up from minus infinity to 0, and then it's concave down from negative infinity, or 0 to infinity. Now, note that there are no mins or maxes in this case, unless, yeah, I don't think that you would be able to find any, like if you do that. Unless you were to close it on an interval, then yeah, you would probably see something like that, like a min or a max. But in this case, there's not. Okay, so we found our intervals of concavity for this one. Now, let's say, for example, that we look at finding the point of inflection. The point of inflection is whenever the function is equal to 0 at the second derivative. So you have x cubed minus 2x plus 3, or not plus 3, but minus 3. Now, we just need to find the first derivative. So the first derivative is 3x squared minus 2. Then from here, we take the second, which this will be just 6x. That tells me that basically that x has to be equal to 0. Why? Because remember that when you set it to 0, that's where it's going to give you an inflection point. Now, if we plug in a value Okay, so if we plug in a value such as 0, or less than 0, so like -1 and 1, well, what you're going to have is that that's going to be negative, and that's going to be positive. So essentially we have that the point of inflection is at 0, comma -3. Okay, so we have that this is the inflection point. And then we also have that it's concave down from -infinity to 0, and that it's concave up from 0 to infinity. Now, of course, if you wanted to look at the graph, you can do that, but just be careful in figuring out like which one is which. Now, we can also look at another one of which that we have that we want to basically kind of like find the same thing. So, right. So let's say that we have, well, how about this? Let's consider that we can look at the second derivative to help us figure out a few things. So for the second derivative, we actually have that it tells us more besides points of inflection. So notice that I have a max right there. I have a min, I have a max, and I have a min. Now, one thing that you'll learn is that essentially at the second derivative, if it's less than 0, that implies that you have a max. If the second derivative is greater than 0, that implies that you have a min. But unfortunately, if it's equal to 0, it's inconclusive. Okay, now, in this case, this is what I wanted to do with that example. I want to look at an example of where we go ahead and we find our respective mins and maxes. So let's say that, we have a function of which is called y equals 3x to the fifth power minus 5x cubed plus 3. So we want to find all extrema. But let's use the second derivative. So y prime is equal to 15x to the fourth minus 15 x squared. Now notice that this is going to give us x squared multiplied by, let's say 15, multiplied by x squared minus 1, which basically just tells us that this is 15x squared multiplied by x minus 1 multiplied by x plus 1. Now, this is basically telling us that we have 3 extremas, possibly. So we have the critical points are 0, -1, and 1. But let's say that we go ahead and we find the second derivative. So we find the second derivative, which is basically just going to be 60x cubed minus 30 x. Now we can take this out and just say, well, we have 30x times 2x squared minus 1. Now, basically that's going to tell you that you do have like some points of inflection, but notice that if you do find the points of inflection, you're going to find that 0 is one of them, which means that 0 is actually nothing. And then you also find plus or minus root 2 over 2. Okay, now we didn't really need these, but I just wanted to put it there so that way you would know that 0 is not anything because it's a point of inflection. So you have 0, and then you have root 2 over 2, and then you have negative root 2 over 2. Now, in reality, technically, we don't really need to do anything because all that we need to do is just plug in 1, 0, and negative 1. So like for example, if we plug in negative 1, we have that y prime of negative 1. Well, that's going to be negative 60 plus 30, which is actually less than 0. If I plug in 1, well, that's going to be 30, which is greater than 0. So I have that 1, 1, or sorry, 1 is a min. So I have that at 1, and if I plug in 1 back into the equation, I get actually 1. This is going to be a min. The reason that it's a min is because it's greater than 0. But then if I plug in negative 1, notice that we found that negative 1 is a max. So we have that, let me just write it over here. This is a max, and this is a min, because the second derivative. So when we plug in negative 1 into the equation, you're going to find that it's going to give you 5. So in this case, this is going to be a maximum at 5. Now, interestingly enough, if you go ahead and you try to graph this equation into, let's say, like Desmos, so we have y equals to 3x to the 5th power plus, not plus, but minus 5x to the 3rd power, and then we have plus 3. Well, see like how 1, 1 is our minimum, 0 comma negative 3 is nothing, but then negative 1 comma 5 is our maximum in this case. So we basically find that the second derivative test does allow us a whole lot. Now notice that I kind of did waste time on figuring out the points of inflection and then making this interval line test, even though I didn't really need it. But that's just to give you an idea of like, if you did need it for whatever reason, you know that after this you would just set up your interval line test and then do your plugging your points. But one thing that I want to make note of is that because I already found my minimum and my maximum, the point of this chapter is to kind of be able to um, use the test to be able to tell like what the function does. So notice that we already figured out the minimum and the maximum. So what that means is that technically we can actually reverse the process. Minus, 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 plus, 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 minus, minus, minus. How did I do that? I did it based on the fact that this was a minimum, and this right here is the first derivative, and this had to be a max. Notice that basically this tells me that the function looks something like this, where it decreases, increases, decreases. So in that case, I already kind of have an idea of how the graph should look, which that's what we figured out over here in terms of like, figuring out what that looked like. It does look a little different though. Oh, I think I wrote that. Yeah, it's backwards. Um, okay, I'm sorry. We got to be careful with that. So we have that this should be the maximum. So that means that this is plus, 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 minus, 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 and then plus, plus, plus. Okay, so that means that the graph looks something like that, down and up, and that was our max, and that was our min. So that means that we know what the levels of increasing, decreasing are based off of the first derivative. But notice that it doesn't really look technically like the way that it should, and that's mostly because of the fact that when it passed through 0, that's where it kind of like wiggled through it. So it was like minus minus. So over here we should have a turning point in actuality. But that's kind of like what this chapter basically is being able to use the first derivative test and the second derivative test and be able to like reconstruct the graph like if you were trying to look for a sketch. Now, I want you to go ahead and try y equals 2 times x squared minus 4x plus 3 squared, and try to see like if you can, find those points of inflection, the extremums, and the levels of increasing, decreasing, and then you can even find y-intercepts if you want, and also x-intercepts if you'd like. But in any case, like that's the whole point of this section. So by the next section, you should be able to kind of sketch the graphs based off of everything. So with that, just make sure that you're clear on that the first derivative basically allows you to find all extremas and the increasing, decreasing, and that the second derivative, it has to do with concavity and basically like points of inflection. And then you can also use it known as the second derivative test. So in some way, once you get kind of better at this, you can actually use the second derivative test to tell you everything in actuality. And that saves you enough time because see like how I reversed the process just off of using the second derivative test.